Welcome to Pod 4 Journal Club. Today we're diving into a really cool new study. It's all about one of the most human things we do when we problem solve, that aha moment. You know, that sudden spark of insight. Well, researchers are actually trying to teach AI how to do that. And honestly, the results could change everything.
You know that feeling, right? You're staring at a tough math problem, you've tried everything, and you just hit a wall. You're completely stuck, and then, out of nowhere, bam, an idea just clicks into place, and suddenly the solution is crystal clear. Well, that little moment of insight is what separates just crunching numbers from real mathematical reasoning. And it turns out that's exactly where even our most powerful large language models, our LLMs, totally get stumped. I mean, they're incredible with words, but when it comes to complex, creative math proofs, they often get just as stuck as we do.
All right, so here's our game plan for this explainer. First, we'll dig into the AI's insight problem. Then, we'll look at how the researchers trained an AI apprentice. After that, we'll check out the results, the aha moment. We'll also talk about what we still don't know and wrap up with the future of AI reasoning. Let's get into it.
Okay, Section 1, the AI's insight problem, the missing spark. So first things first, let's really get a handle on why AI struggles with this stuff. What's the missing spark? You know, what's preventing it from making those creative leaps? Turns out, it kind of starts with how we're asking it to solve problems in the first place.
The researchers are focused on a task they call Informal Theorem Proving. Now I know, that sounds super technical, but don't let the name fool you. All it really means is teaching an AI to write out mathematical proofs using natural language. You know, just like how a student would write one in a textbook, with regular words and standard symbols. This whole approach is clever because it plays to the strengths of LLMs, which are all about language. But at the same time, it puts a big spotlight on their biggest weakness, that creative reasoning part.
Okay, check this out. What's so cool about this image is that it literally lets us see where the AI is getting confused. The researchers took the model's output and highlighted the spots where it was most uncertain about what to write next. And look, the warm colors, the oranges and reds, that's where the uncertainty is highest. And guess where those spikes happen? Every single time, it's right at the moment that requires a leap of insight, the aha moment. The rest of the proof, you know, the simple logical steps, no problem at all. It's these critical creative jumps that completely trip the model up.
So, the researchers figured out that these aha moments aren't just some random magic. They actually broke them down into three main categories, what they call core techniques. First up, there's construction. This is where you have to introduce something totally new, like inventing an auxiliary function to help you out. The second one is a theorem call. That's when you realize, oh, I need to use Cantor's theorem here, or some other result you already know. And the third is mathematical transformation, which is super clever. It's when you recast the whole problem in a new light, like turning a tricky geometry problem into a much simpler algebra problem. These are basically the creative power tools in a mathematician's toolbox.
All right, Section 2, training an AI apprentice, a human-like learning journey. So that's the big question, right? How in the world do you teach a machine to have these moments of insight? The researchers quickly realized that just feeding the AI thousands of completed proofs wasn't going to cut it. It needed to learn the thinking process behind the proof. And their solution? Well, it's surprisingly human.
They tackled this with two key innovations. First, they built a brand new dataset called DeepInsightTheorem. What they did was take over 100,000 top-notch math proofs and, pretty cleverly, used another AI to help them label everything. For every single proof, they pulled out those core techniques we just talked about, and they also created a high-level proof sketch, like an outline or a plan. And second, they came up with this awesome training strategy that's designed to mimic how we humans learn a skill, going from a total beginner all the way up to an expert.
And this apprentice-to-expert curriculum is really where the magic happens. It's a three-step process. In step 1, the apprentice stage, the AI just learns the basics of writing a proof by studying completed solutions. Pretty standard stuff. Then, in step 2, the journeyman stage, it learns to take a high-level plan, that proof sketch, and fill in all the details to make a full proof. It's kind of like learning to follow a recipe. But step 3, the expert stage, this is the real game changer. Here, the model learns to look at a problem and first predict which of those core techniques it's going to need, and only then does it build the sketch and the final proof. It's literally learning to have the aha moment before it even starts writing.
Okay, Section 3, the aha moment. So this brings us to the part we've all been waiting for. This whole training setup sounds great in theory, but did it actually work? Let's take a look at the results.
First off, I just want you to appreciate how tough these problems were. We're not talking about your high school algebra homework here. On average, each proof in the data set required about 3.6 of those core technique insights. And if you look at the chart, you can see that a ton of them needed 4, 5, 6, or even more of these creative leaps. This is seriously challenging Olympiad-level math.
And wow, the results really do speak for themselves. This table gives us a direct head-to-head comparison. The baseline is a model with standard training. The three-stage line is their new insight-focused method. And just look at the scores. Across every single one of these benchmarks, which by the way are all based on incredibly hard math competitions, the new method gets a really significant performance boost. That's a huge, undeniable win.
And this wasn't just a one-off fluke with a single model either. These graphs here show that the same exact trend holds up across a bunch of different AI models, even at different sizes. The dashed line is the old way, the baseline performance. The solid line is their new insight-driven method. And you can see it plain as day. In pretty much every single case, the solid line is higher. This thing works, and it works consistently.
Section 4. What we still don't know. The reality check. Now, in the spirit of a good journal club, we've got to have a little reality check. These results are amazing, for sure. But it's also really important to be clear about what this research doesn't solve and what the authors themselves are upfront about as limitations.
So the main thing to keep in mind here is that this entire performance jump comes from just one thing: a smarter way of doing what's called supervised fine-tuning, or SFT. That's it. They haven't even tried to combine this yet with other advanced techniques like reinforcement learning, which can often be even more powerful. So while this is a massive win for this type of training, it also kind of hints that there might be even more performance just waiting to be unlocked if they start combining these different approaches down the road.
Okay, Section 5. The future of AI reasoning beyond imitation. So let's zoom out for a second. What does all of this really mean for the future of AI? Because this is about way more than just getting better scores on math competitions. This could be about a fundamental shift in how we build AI systems that can actually reason.
You know, for a while now, there's been this big worry that LLMs are just stochastic parrots, that they're just mindlessly copying patterns they've seen in text without any real understanding. Well, this research offers a path to something more. By explicitly training the AI to have these moments of insight, we're basically teaching it to come up with a high-level plan before it starts writing. And that moves it away from simple imitation and towards a process that looks a heck of a lot more like genuine, structured thinking.
And I think the authors themselves really nail it with this quote. They say that by explicitly training the model to acquire proof insight, it enables it to move beyond mere text imitation toward more faithful, insight-driven mathematical reasoning. And that, right there, is the whole ballgame. This is a method for teaching not just the final answer, but the actual how and why behind discovering that answer in the first place. So that leaves us with a pretty mind-bending question, doesn't it? If we can teach an AI to have mathematical insight, what other human cognitive skills are next? Scientific discovery? Breakthrough engineering? Creative writing? I mean, where does it stop? Let me know what you think down in the comments. And hey, if you enjoyed this breakdown and want more deep dives into the research that's shaping our world, make sure you subscribe to Pod 4 Journal Club. Thanks so much for watching.